Dr. Mohamed Alouini. He has been very much involved in IEEE Future Network Initiative, Connecting the Unconnected. So we have the pleasure of introducing him. You're what, 6 hours ahead? 7 hours? I don't know what is the time there. So he received his PhD in electrical engineering from California, Caltech. Served as a faculty member at University of Minnesota, then in Texas A&M University at Qatar, before joining King Abdullah University Science and Technology, KAUST in 2009. He's now a distinguished professor of electrical computer engineering. He's an IEEE fellow, also fellow of Optical Society of America, OSHA, is now Optica. So with that, Slim, you can carry it on. You have 20 minutes.
Okay. Thank you, Ashutosh, for that.
Share. Yeah. Thanks.
Yeah. Okay. Thank you, Ashutosh, and Marjorie, the organizer, for inviting me and giving me this opportunity to share some of our thoughts on beyond 5G and 6G. I really enjoyed all the talks throughout the day. I have been following online, and I hope that I will have the opportunity to attend in person the next G Summit. So let me share my screen. I hope you all see my screen.
It's coming up. Yeah, it's up.
Okay.
So you have about 20 minutes, Slim. Yes.
Sure.
Thanks.
Sure. So I think there is some interesting connection with what Sumit presented and and also the last talk from Hughes. So talking about free space optics and also satellite communication. So the theme is going towards extreme band communication, and I'll go very quickly over the first few slides because we all know that we are going through this 10-year cycle as the 5G is being deployed. Obviously, there is quite a bit of activity, and today summit is a reflection or is an illustration of this really very interesting brainstorming and research activity happening worldwide to make beyond 5G and let's say 6G a reality. And of course, 6G is about super connecting the connected by increasing the data rates, increasing the capacity of coverage, and of course reducing latency. And we heard about a lot of the nice things around this today. And one thing that of course we have to remember is that this beyond 5G or 6G type of technology will have to operate still within the limited spectrum that is getting more and more scarce. And when we talk about spectrum, often we are talking about the lower part of the spectrum. The spectrum is much wider than that. And that's why one way to kind of present why we need to go to extreme band communication, because we are often after this metric, this area spectral efficiency, bit per second per meter square, that you can kind of divide in 3 factors. And there is, of course, research in trying to make things more spectrally efficient at the physical layer. There is a lot of research on densifying the network by going towards smaller cells and maybe spectrum sharing type of approach. But also, and that's the today focus of my talk, is to go towards the higher part of the spectrum. And in particular here, I'm talking about terahertz communication and optical wireless communication. This in view of the fact that already millimeter wave was a big part of 5G research. So the next step is to go to even higher frequency band. So terahertz has been quite a bit of an interesting topic for many of us. It has this interesting characteristic of going to such a small wavelength that you can view it as a meeting point, not only for communication, but also a meeting point where the classical application of terahertz, which is sensing, imaging, and localization, can be merged with communications. But of course, it comes with its challenges, the challenges that we have been already facing in free space optics. I will talk about that in terms of pointing, in terms of sensitivity to channels. And actually, in millimeter wave, we have seen some of these kind of also pointing problems, but they are going to be more accentuated in the terahertz band. Now, the other kind of interesting technology when you go to this extreme band is the well-known free space optical communication, and there has been some question after Summit talk about that. It's a technology that is in a way mature. It has a lot of benefits in terms of having access to an unlicensed band, providing super high speeds, being able to be deployed on a green field in order to kind of be used for, let's say, wireless backhaul solutions. But it comes also with its own challenges, in particular, very much sensitivity again to pointing and sensitivity to atmospheric turbulence and more generally to weather condition. And here I'm talking about fog, or if you're talking about ground to space type of applications, clouds, for example, can be also a big factor that can affect the reliability of free space optics. Now, what I would like to show is how actually these two extreme band communication can be kind of coexist or can work together to essentially improve the overall performance of the system. So one way to marry this technology is to use them in cascade. What do I mean by that? I mean that basically, you can, for example, have, and that's kind of research that we have done like over the last few years, but I will explain how we kind of followed up on that more recently. You have typically kind of, let's say, millimeter wave users that are being operating at a very high speed, and then eventually they need to be multiplexed, and you need like basically a backhaul and aggregate kind of link that kind of combine all of these high speed coming from users. And now, if you don't have a fiber optic, obviously, and you want to have that high capacity link, you may want to go for an FSO link. This can be done obviously from a downlink perspective, where you have the first hop being RF and the second hop FSO, and it can be done the other way around, where basically it's more broadcast, where the first hop is FSO and the second hop is RF. But the idea here is the FSO link is acting as an aggregate link, combining the data rates coming from different millimeter wave users. Now, more recently, we looked at an extension of this work, where basically we want to kind of make the FSO link more reliable. As I mentioned earlier, one of the main issues behind FSO link is essentially its sensitivity to turbulence, to weather conditions. And one way to make this FSO link more reliable is to use a terahertz backup link. So the backup link is there so that basically terahertz can come close in terms of speed capabilities and FSO, not exactly the same, but it can approach the FSO speed capability. So the idea here is by default, you'll be using an FSO link backhaul, and if the FSO link fails for whatever reason, for bad weather condition, for turbulence type of atmospheric turbulence type of issues or pointing problems, then you can switch to the terahertz link. And then this kind of link is acting as a backhaul again to multiple users being connected, let's say, through millimeter wave communication. We are talking about here a backhaul link of 50 to 100 meters apart. We assume that the terahertz link can be a MIMO link, so basically try to match the capability of the FSO link operating in 180 gigahertz. And we assume that the user are simple users with a single antenna. And that was a kind of system of interest. And in this context, we looked at two switching algorithms. So the first switching algorithm, without getting into much mathematical details, it's a very simple kind of switching algorithm where by default, we are going for the FSO link. And if the FSO link SNR falls below a certain desired threshold, then you switch to the second link. This work is done, by the way, in collaboration with Ericsson research team. And one of the main concerns they had is that essentially this kind of switching, especially when often what happens, you have switching back and forth between the FSO and the kind of RF, in this case, terahertz link, is not very beneficial, in particular if you're operating at super high data speed, at terabit per second or multi-100 gigabit per second. Every time you switch, it's a mechanical switch, you are losing a lot of packets. And basically, especially if you are in this kind of situation where the link is not very stable and you keep kind of switching back and forth between the FSO and RF link, the so-called ping pong effect, this is not much helping the overall performance of the system. So the solution to that is that we developed another kind of switching algorithm that has some memory, let's say, a kind of in its design, which means that you look at a trend. You will switch from an FSO to terahertz only really if you are going to a bad channel situation for FSO. This is to avoid, again, the so-called ping pong effect, and you don't have to switch back and forth if the channel tends to be kind of unstable. What we showed is that using this type of switching algorithm, which is like a softer switching algorithms, you don't lose much in data rate. Actually, you can do as well, and you gain a lot actually in the switching rate, which means you minimize the frequency of switching between your FSO and your terahertz link. In terms of performance, we showed, for example, when you look at the outage probability, as an example here, the terahertz link performance is in blue, the FSO link is in red. Together, they can give, because it's a hybrid link, they give a much better performance. Now, the end-to-end, if you take into account the millimeter wave, depending on the number of antenna you're using, it might be the limiting factor if the millimeter wave is subject to strong fading. But if you improve the number of antenna on your access link, especially from the base station, you can improve, and you see here in green, theoretically, and in stars by simulation, that if you increase the number of antenna in the access links, you can improve the access link and eventually improve your end-to-end link performance. So this is my final kind of figure here for this particular project, where we show the difference between hard versus soft switching, and we show that in pure outage probability we don't lose much, but actually we have shown some other results where we are minimizing this kind of switching rate, which means we minimize the number of packet loss during the switching time. But in terms of performance, although hard switching is, in a way, if it's done ideally, it should give you much better performance than soft, but actually the performance is very similar. So now let me switch to the second topic of my presentation, which links to some of the questions that came out of after Summit talk, is hybrid terahertz FSO system in the context of non-terrestrial network. I have been always saying that hopefully beyond 5G and 6G is not only about super connecting the connected, but also about connecting the unconnected. And when we talk about connecting the unconnected, the Holy Grail is about providing a high quality of experience for areas in the world that basically suffer from, let's say, a low income or a low population density areas. So you want to provide good quality that is actually at low cost for this particular area, in order to achieve this interesting and prophetic visionary statement made by Tesla about 100 years ago. And when we talk about global connectivity Holy Grail, one of the key words, and we have seen some of the talks today about that, is the integration of space, air, ground networks, or if you will, this kind of general theme of non-terrestrial network. And when we talk about non-terrestrial network and integrate space, air, ground network, we talk about satellites, of course, for space. We talk about drones and HAPS, high altitude platforms for air, and we talked about classical ground networks that have to be there as a way to user to access your ground network. But the difference between, I think, what we are seeing today and what we have seen in the age of Teledesic and Iridium is we want this to be transparent to the user, so we don't have a special phone or special device to connect to space. The connection to space and air is happening through ground access points. So in this context, again, how extreme band communication can help. It is well known that FSO is very hard to beat in terms of capacity and the data rate that it can deliver. But again, FSO, even in the context of ground to space, can suffer from strong turbulence, in particular in the atmosphere, the 21st kilometer of the propagation path between the ground and space, or the air part of it, basically. And as such, you need, again, to have an RF backup link. Now, more recently, last year, there has been some proposition to use HAPS as relay. And the idea here, it's a nice idea, is essentially, since most of the turbulence is happening in the atmosphere, then a HAPS at 20 kilometer altitude can be used as relay that can clean up, in a way, the signal, decode and forward, and then even if you have to go through thousands of kilometers, through the distance between the hub and the satellite, the channel is much more stable, and there is no much turbulence you have to deal with. So the HAPS is there kind of to help clean up the signal, and send it in a clean form to the satellite. Now, you can, of course, add to that backup RF link. Now, some of the extra work that we have done on that is to try to optimize the position of the hub. And our proposition is actually quite simple. Although naturally, when you look at this kind of geometry, you think maybe that the best position that the hubs should be at is this position, you know, where the hubs is midway between, or like basically on the line of sight, the direct line of sight between the optical gateway station and the satellite. It turns out that actually, if you want to minimize the amount of turbulence that the signal goes through, it's better to minimize the base distance that the signal go through in the atmosphere, which means actually the best way to proceed is to put the hub basically on the top of the optical gateway station, because you minimize this distance between the optical gateway station and the hubs, and as such you minimize the level of turbulence, and then of course you have to go through a longer distance, but actually it's a clean type of channel environment for the FSO link, which means that this can give you some gains, and that will be demonstrated. You can always back up this link with an RF link in case the FSO link is still established to strong turbulence. Now, what
5 minutes.
Yes, what you have shown based on this design, if you look green as being your benchmark, this is basically a standard, let's say, FSO RF link directly from the ground to satellite. If you go with this kind of proposition paper published last year, and you use the hubs, then actually you get the 4 dB gain. Now, with the optimization of the position of the hubs, we basically try to minimize the effect of atmospheric turbulence, especially if you're dealing with strong atmospheric turbulence and you are operating at a strong zenith angle. Then you get a 19 dB gain compared to this reference point. You back up that by an RF link, you get a 2 dB extra gain. So 21 dB gain just by optimizing the location of the hubs and minimize the effect of optical turbulence. Now, final 2 slides. So obviously, you can kind of, it is of course not desired to switch to the RF link, because the RF link will be operating always at a lower speed than the FSO link. So our ultimate kind of system is a system that offers a 3-way diversity type of let's say scheme. In other words, by default, you go through this decode and forward through the hubs. If it's not good enough, you go through a direct path between the optical gateway station and the satellite, and the advantage of that is that you have a diversity of order 2, and on the top of that you maintain high-speed connectivity. Now, if both first links fail, then you go and switch to the RF link, which maintain connectivity at the lower speed. Now, this whole thing has been analyzed. What we have shown is that essentially, of course, if you look at the average probability of error as function of the zenith angle, which is, like the angle between the ground station and the hubs, with our proposed scheme, because we force the hubs to be on the top of the, let's say, of our optical station, is insensitive to zenith angle. This fully kind of integrated system where we have the 3-or diversity, obviously it's sensitive to zenith angle because you switch from like a relayed system to a direct FSO system, and as such, as zenith angle kind of increases, you tend to converge to our initially proposed solution. But initially, you get quite a gain because you have an extra diversity gain. And then one of the beautiful things that we can show with our ultimate scheme is that the probability of RF link usage is much lower, which means with the integrated Satcom system, and that's good, which means most of the time you'll be using either the first FSO link or the second FSO link, regardless of the zenith angle and the low kind of range of zenith angle. As zenith angle increases, you tend to converge to our original solution. So again, the idea here is to show how FSO and RF can work together to kind of make the link more and more reliable. So with that, I would like to thank you, and I will be happy to take some questions.
Any question here on the floor? So while we're waiting for folks online, I have a question, Slim. So I know you initially tried to see how it could be useful, and then you made a reference to connecting the unconnected. I know you have done a lot of good work in that area, and you also know IEEE, we recently last year had a CTU challenge, right? I know, in fact, Dr. Manisha Ghosh, she was in our knowledge partner advisory board. So some of this work you are talking about, how this could be used to help the folks who do not have connectivity, right? 50%
Yes.
of folks,
Yeah.
yeah.
Yeah, I mean, that's the idea is if really you want to provide connectivity to these remote areas, as you know, it doesn't make much business sense to kind of lay fiber optics over hundreds, if not thousands of kilometers to reach these remote, sparsely populated area. So obviously the way to kind of reach this area is through aerial solution. So this aerial solution, depending on, you know, how far they are from urban environment, from internet point of presence, it can be HAPS, it can be a satellite, it can be LEO mega constellations. You know, there are a variety of aerial space solution, and I don't think there is one size fits all type of solution, but all of these aerial solutions are hopefully going to be there to help connect more of the unconnected. But you still need high-speed communication in the feeder link, because again, you're aggregating users coming from different locations, operating, you know, at a relatively high speed. If you talk about decent internet connectivity, and you need to kind of make sure that all these users are accessing the internet, and I mean accessing through a point of presence, which means you need a feeder link. And the feeder link, we propose FSO or a FSO / RF kind of a hybrid system to act as a feeder link.
Thank you, Slim. Again, let's give a hands to him. And